This lecture finishes our exploration of artificial intelligence. Within it, we're going to have a very brief look at some forms of tactical and strategic artificial intelligence. Certainly when we're thinking about AI at this particular level, it is at the upper level. It is about making reasonably long-term plans or trying to ponder and to take into account what you might characterize as the big picture, and then to make some decisions on this. There's an awful lot you can cover within this, and there are multiple techniques. So what we're going to explore are a few techniques that build upon the types of pathfinding that we've looked at. We'll have a look at how we can measure influence, which can then be used to drive a lot of subsequent equations. And we'll spend a little bit of time having a look at board games. It's been a style of game that we haven't really considered much to date, but AI plays a really important part in most board games in terms of providing an engaging experience to the player. But we'll start off first of all with sort of a definition of what it is we're talking about here. So when we're thinking about tactical and strategic forms of AI, they are ones that, as I mentioned here, to drive a tactical assessment of some situation, possibly using incomplete or probabilistic information. That's an important characteristic of many forms of strategic or tactical AI. There will be certain things you will know, there are certain things you will not know, or there may be a notion of probability of chance coming into it, and you have to reason somehow under this uncertainty. And another characteristic of not all, but most forms of tactical or strategic AI is that you are dealing with collaborations between objects. So often it is, as mentioned, looking at the big picture and deciding what a group or a collection of objects characters should do in terms of their particular response or activity. Not every game needs to have this. In fact, most genres don't have it. But for some games, it is very important by way of providing a good play experience or game experience to the player. We'll start off having a look at some illustrations of tactical or strategic AI. And we'll start off with tactical. And here we're going to build upon the notion of waypoints. So waypoints we looked at before in terms of pathfinding as a way of representing regions, important regions within the game where we can walk from one waypoint to another waypoint. And for us, that point, a waypoint, was simply just a point, a location, and it was connected to other points, and that's all we needed to know. But we can enrich this if we want to, and here we have an illustration of sort of a top-down view of an interior room where we might have some tables, some plants, some sort of dark shaded areas, and if we wanted to, we could attach waypoints to this, sort of really building upon that. So types of things we might have might be C for a cover point. So we would put that if a character wanted to get itself into a position of cover, then we would be indicating that this waypoint provides good cover. We could also identify, say, for example, reconnaissance points, points where there's good line of sight. And again, if a character felt that it wanted to find itself in that position, it would know where it needed to navigate to in the level. Beyond that, we could identify the shadowed locations, so the areas or the regions of the environment that has low visibility associated with it. We could do power-up spawn points. You could have whatever types of things that you want to have within it. We'd even identify bad locations, exposed locations within the environment to say that these are potentially dangerous. You should be cautious of using them. So this is an illustration of how we have started to embed in not just simple points in our level, but talking about the characteristic, the advantages, the disadvantages of those points. Now, how we generate those points, so tactical locations can be either set by the designer, you get a person to look at it and go, well, I think this is this type of location, or you could actually derive it from game data. So if you get a lot of people to play the game, you can identify certain areas where certain things happen, or you could do an evaluation of how lit the environment is. So there's different ways of deriving that information. If we plug it in, the nice thing is that all of the pathfinding algorithms that we looked at, particularly A*, when we're calculating either the given or the estimated cost, the heuristic cost, we can take into account weights for the value of the different cells. So if we had information pertaining to how well lit a cell was, then a cell that was very well lit, we would give it a high movement cost in terms of our pathfinding. It's an area that we would try to avoid unless it was really essential for us getting to our destination. Doing that means that we can take the exact same pathfinding algorithms we had before and make them tactically aware in terms of the types of paths that they're being asked to generate. Another related item to this is the idea of an influence map. So in this case here, it's often used at the highest level in terms of strategic analysis. We want to take a step back and to somehow look at all of the area that's in play and to identify their regions which are controlled by one player, regions controlled by another, where you might characterize the front line to be, if there's an opportunity to expand into certain areas. So an influence map will give us quite a rich source of information that enable a lot of those other higher level decisions then to be informed, to take the amount of influence that has been spread into account. Multitude of uses, and actually influence maps are fairly easy to generate. In terms of how we do that, we start off with the notion that each entity associated with a certain player or a certain side extends or influence spreads out from it, so it controls a region or a zone around it on the map. And the further you go away from it, then the smaller that influence is. But it's additive, so every single entity is adding its influence in, so we're looking at the sum influence that is generated. You may have certain objects, for example walls or rivers or other things that, if you like, block influence from passing through them or somehow curtail or reduce the spread of it. So we can, an influence, as mentioned at the bottom, generally decays over distance. We give you an example here. So notionally in this grid-based setup, we have two sides, a white side on the left-hand side of the diagram and a black side or dark side on the right-hand side. For the white side, they have a castle down in the bottom left-hand quadrant, sort of in green grass, and there's a blue river then that goes around it. There's a bridge notionally drawn to the right of that white castle, and sort of the dark grey areas, we're imagining they're like a mountain range or something. On the dark side, the black side, we have a black castle up in the top right, and an entity, a character down in the bottom right. So we want to run or to build up the influence map for this group of objects. Different ways we could do it. So for example, the character at the bottom, we could assume it has an influence of 3. So at its heart, that's the influence that it exerts. And then we decay that the further we go out. So you can see as we're moving along the grass, moving up, we go from 3 to 2 to 1. As the influence passes over the water, it declines more strongly. So there we're dropping 2 off, so it goes from 3 to 1 to nothing in the other side. So that measures, if you like, the influence of that particular character. We can do the same, for example, the city, the castle at the top. There we're assuming it exerts a stronger influence of 5. And if you look straight down from 5, going down to 4, going down to 3, to 2, to 1, there we have a cell whose influence is determined both by that castle and by the entity. So the influences add, they're cumulative. You can see here that again for our mountain range, we're saying it blocks influence very effectively. So we have a drop of 3 from one square to the next. Now having done that, we can do more or less exactly the same thing with the white castle. So again, influence of 5 extends out, the water blocks it by 2, but we have a bridge, so we're allowed the influence to pass over the bridge, so it goes from 4 to 3 to 2 to 1 as you go across the bridge. And there you can see we have some squares where there's mixed influences. There'll be some white, there'll be some black. Now, having gone through all of the objects that cast or emit influence and having built up this representation for the level, we can do lots of easy analysis that provides quite useful information. So for example, all of the squares that only have white influence, we can define that as the region that white safely controls. Likewise, all of the squares that have dark or black influence, we can define that as the region that the black player safely controls. The cells that are left then are going to be a mixture. Ones which are mostly white with a little bit of black, these ones we can sort of say are contested but are controlled by the white player. And likewise for the other side, for the dark side, ones that are mostly dark with a bit white, we can say they are contested, mostly controlled by the dark player. Where we have equal influence within the cells, these in some sense represent our front line. They're contested, no man's ground. So that's where a lot of the contention currently is at. And cells which have no influence exerted over them, these provide a good illustration of areas where if you wanted to build a new city to expand into, you would be looking for those particular regions. So influence maps, quite quick to calculate, very easy to calculate, and provide access to quite a lot of useful types of information that can help inform and derive some type of strategic analysis. Now, having looked at that, there's a couple of illustrations. There's 101 different types of tactical or strategic analysis or forms of AI you could use. This just flavoured it slightly. I'm going to move on to have a look at board games in terms of the AI that they use. So board games, just an historical aside, was actually the very first application of AI, was to get an early computer to play a basic board game, be it nuts and crosses, tic-tac-toe, or something like checks or drafts or chess or something of that nature. Most board games, certainly most classical board games, they assume you have two players, not all, but I mean most of them, and you can generally build upon these algorithms to cover for more. Depending on the type of game, most games player take a move or have their turn, and then it sort of swaps about, so it alternates from one player to the next. There's a class of board game known as a zero-sum game, and that covers most of the classical games. So a zero-sum game is a game where if you win and I'm playing you, it means then that I've lost. Or if I win the game and you're playing me, then it means that you've lost. So it's zero-sum. If one person wins, the other opponent loses. You can't have a situation where both people win or both people lose. It has to be one and the other then automatically loses. It's zero-sum, so sort of win balances out the lost. So it covers most of the classical board games, doesn't cover some card games which can be played against the house. Now, the nice thing about a zero-sum game is you can view it in two ways. If we're trying to do AI, I can either have a form of AI that tries to get me to win if I'm the AI controlled player, or I can swap it around and I can say I'm going to try to get you to lose. So in both cases, it has the same outcome, that ultimately I will win and ultimately you will lose in terms of this particular illustration. So zero-sum, nice concept too, and it's going to come into one of the algorithms that we will have a look at. If you have a non-zero-sum game, so if you're playing against me in an area where it's not sort of win-lose, but two people can win, two people can lose, you should only focus then on winning yourself. It doesn't matter what I do in that particular sense, or it may not matter. Complexity can increase very notably whenever you have more than two players, particularly if they are allowed to cooperate, to form temporary alliances, to gang up, to work together, all in terms of some greater common goal that they have, and then later on, they can all fall apart. So more than two players does get a little bit more complex. Another entity that comes into this here is the notion of information, if it's perfect or imperfect information. And a lot of board games, there's perfect information, which is to say you can look at the board and you can see every single piece that is in play, and all of the information that's associated with it is available and displayed there. Imperfect games are ones where some of the information is hidden. So either I don't know what you have in your hand, or a dice roll is involved where the dice may come up with a different number. That's unpredictable. There could be a range of outcomes, so we have imperfect information. Maybe some things we know, some things we don't know. We've got to try to take that into account. Now, we're going to have a look at an algorithm, and most of what we're going to assume here, because it applies to most of the classical board games, we're interested in a two-player, perfect information, zero-sum game. So two people playing where they can see all of the relevant information, and at zero-sum, there'll be a winner and there'll be a loser between the two pairings. Now, given that, we want to try to work out, well, how can we create a form of AI that could hopefully play this with the user? And here, another notion, the notion of a game tree comes into play. So you can see noughts and crosses, or tic-tac-toe, an example over here. And we can assume this is a game state. We have some of the tiles being marked with an X and an O and some sort of blank. What we would have in the game tree at the next level down shows all of the possible next steps in the game. That we assume X went first, O went next, and then the next level down we have X, and we're showing all of the different moves where the X could be placed on the chart. So that gives you a layer down. Again, that can be extended out for each of those game states. Again, you can carry on. Imagine, well, where would O put his or her particular counter? And carry on. The branching factor is an important measure of just how complex this is. So effectively what that stores is at a particular level just how many different moves you could make, and they all correspond to different branches then within the tree. And the more moves you can make, then the bigger the size of the tree is going to be, the more difficult it will be to do a brute force search. Okay. If we're talking about a zero-sum game, and given the game tree structure, we can have the notion then of a score being associated with the tree. If you get down to a leaf node in the tree, it's game over. It means then that the score is going to be either +1 or -1, depending on whose perspective it is in terms of the wind being associated with. If it's somewhere mid-tree, it hasn't yet finished, you can have a fractional number coming out. So it could be 0.8, it could be -0.2, it could be 0, meaning nobody has a particular advantage. So in that sense, you have a numerical value that tries to capture just how good a position each of the players are in. For a zero-sum game, ultimately things are going to have to add up to 0 in terms of always being a winner, always being a loser. Now, given that tree-based structure, what we want to do is to have a process that says, given this board state, tell me the next best move. What move should I make to make it more likely then that I'm going to win the game? And in doing this here, you have probably the most difficult bit coming in. It's known as a heuristic static evaluation. So this is something that can look at a board that's in play and say that this should be your next move, or here's a small selection of moves that you may want to make. So this is the thing that embodies if you like, the heart of the AI. Again, in terms of making the move and giving a rating to that move, if it's a final state, you'll know who the winner and the loser is. If it's a sort of a mid-game state where you're not predicting all the way to the end, then you'll have sort of a mixed or fractional number being returned that can use to help indicate which move appears to be better. Important to this to note that at this point, the heuristic evaluation function, it is game specific, and different games will have completely different approaches in terms of how they can be played well. So if you're looking at reversing in terms of the slide here, your tactics, your strategies would change from mid-game, where you want to have a small number of counters, all the way to end game where you're trying to maximize them. For things like chess, it can take into things like the tempo of the game, who controls what within the board, piece counts. You can even sort of then tweak these things in terms of preferences and to bring out different personalities. If there's a certain game style or game component that notionally the AI values, it can attach a higher weighting to that in terms of the decision-making process. Now, given all of that, we need an algorithm that's going to help us find what we believe to be the best move. And this is where the notion of minimaxing comes in. So the idea of minimaxing is that you have something that takes turn. It's your turn, then my turn, your turn, and my turn. And during each term, you will either try to minimize something or maximize something. So if it's your turn, you will try to maximize your score. If you're then swapping over to me and thinking about it from your point of view, you want to minimize my score on the next move. So you alternate between maximizing your own score and then minimizing the other person's score, because both of them have the same outcome in terms of one person winning and the other person then losing. And that's the essence of minimaxing, how the thing works. So the minimax search alternates between maximizing the player's score on their turn and then minimizing the other player's score on the opponent's turn. Because you're sort of assuming that the opponent will act to minimize your score whenever he or she takes this move. So you have this here, always thinking about it really from the one score perspective, but I try to maximize it in my go, but then whenever I'm trying to think about what you will do, I will try to minimize my score, because you're likely to, that's what you want to do, you want to have my score to be as low as it possibly can be. What we can do here is we can have a search process. We can look at a number of searches ahead, moves ahead, and pick the best overall move that's most likely to result in a positive outcome in terms of our evaluations. So here's the algorithm. It's going to be a recursive algorithm. It'll go down to a certain distance because these trees can be very, very exceptionally large, where we'll stop and then we'll sort of back up on that. Going to define it, so get best move, it will return a move. You call this, you pass in the board states. This is the current board state of the state of the game, and you say which player is making the move. So we have important to understand whose move we're trying to optimize, to maximize. So the method will give you back the move to make. Inside the method, we have basically the setup for a recursive call. So we're calling Minimax, which is a recursive function. We're passing in the board state, passing in the player. We're passing in the maximum depth that we're willing to search down to and the current depth. So initially it's 0, we're at the top of the tree. That will be a recursive call, it'll finish, it'll return us the move, and that's what we return. In terms of the recursive function, so there you can see we're returning score and the move output. So there's two pieces of information this method needs to output. Tell us a move and tell us what score. Is that a promising move? Doesn't look to be not such a great move. What score is associated with it? We'll be considering lots of different moves, so it's going to be important to pick the move that we think has the best score, going to have the best outcome. So all in that, we're passing in the board state, the player, the max depth, and the current depth. So what we do, first of all, within the recursion is our exit condition. So if we reach a board state of game over, or we've reached our current maximum depth we're allowed to iterate down to, in that sense, we just simply look at the board as it currently stands, we evaluate it. That hopefully will give us a score between positive 1 and negative 1 based on how good we think the board looks to us in terms of the rules that we might, types of evaluation we might conduct to the sort of game mid-play. If the termination or the recursive break doesn't happen, then we're into working out the best move. So we're going to score the best move and we're going to remember it. So we'll have a move, best move, and a float for the best score. The bit after this then asks us whose move is it in terms of playing it, and if the current player is equal to player, then we want to go for a maximization. So our default, our starting max score is the smallest one possible, so any one we consider will give us a higher scoring move. If it isn't the player, then we want to minimize the move in terms of thinking about it from the point of view of what was the player going to do that's going to minimize my score. So there we set our maximum score to max score. We can only go down from there. Interesting finding the minimum score. For each move that's available to us, so for each move in the board, get the valid moves, and you may be more restrictive here in terms of the moves you're looking at, but in essence this goes through each of the valid moves you can make based on the board state. You then recursively call the function and you say, okay, for that particular move, let's make the move. We update the board with that move having been made, and we call our recursive function again. So the recursion then kicks in. We'll consider that. We'll ask, is it the end of the game? If it's not, we'll consider what new moves could we make in this case. We'll take each of those in turn, we'll make them, and we'll push it out again to the recursive function. So you can see that very, very quickly we'll have there's likely to be a lot of CPU resource consumed for most games in terms of going through this space. So there's danger in doing it exhaustively because it probably will kill your performance. And that's why the method above, when we said board state get valid moves, we may want to be slightly selective in the moves that we return, keep it to the ones that we believe are likely to be profitable. The bit at the end basically says, well, you've taken a move, you considered that one, has it resulted in a better board condition, if you like, has it improved upon things based on our current overall best score? So if we find a new move that's going to give us a best score, that's the one we hold on to and we remember that particular one. Very end, we're simply returning the best move and the score associated with it. And again, this is how the recursion knits together. There are various other approaches you can use because again, this is very much a brute force approach and it can kill your performance quite strongly. So some other techniques, use of what's known as A/B pruning, alpha-beta pruning. So this is one where you will prune the tree to remove whole branches from the tree where you're going, nope, that branch isn't going to be profitable. And going that way, it isn't going to improve upon some of the other ones, so it gets to be chopped, gets to be cut. That can have a massive effect, and that's what you should be doing if you want to use this algorithm in terms of the overall speed and performance. We can use fancy things like tables, so we can remember changes that we've made and enable us to do searches quicker within our data structures. We can also mix this with expert knowledge. We could use opening books, for example, in chess, or set plays when we feel that there's an appropriate thing to do. So that saves us then, we have to detect when it is appropriate, but it saves us then rerunning the AI to work out every single time what's the best move. We simply follow that fragment of that script with some updations if need be. So a fair amount in this. We've only really scratched the briefest, or the surface in the briefest of ways. So there's an awful lot of good material. You can look at strategic and tactical AI or board game AI. The course textbook makes reference to a recommended book on AI. Very strongly recommend it by way of getting it, because it'll delve into a lot of the things which I haven't really sort of covered here in this initial introduction.